Well, let's start. Good morning, everyone. First of all, I would like to thank Joan for putting this great setup. I'm really excited about these 2 days, and I'm willing to meet every one of you. I want to exchange a lot of comments, insights during these 2 days. Today, we will present computational processes for adaptive biomechanics. My name is Jesus Marini Parissi. I'm the founder and computational design engineer at Moonrabbit Adaptive Lab. Well, this is the first time that we are presenting in such important meeting, so I will spend a couple of minutes explaining who we are, what we are doing, and why we are doing it. We will talk a little bit about what is our main focus areas, how do we approach project solving, and two study cases in which we will showcase how do we use computational design in problem solving for our clients. Unravel Adaptive Lab. We are an Italian innovation startup formed in 2023 by a multidisciplinary, multicultural team, and we are specializing in the area of computational design for consumer products. Our main headquarters are in Milan, Italy. Our mission is to unleash the potential of emerging technologies and create a bridge between the new and the traditional development processes. We blend different fields of expertise, enabling an holistic approach to problem solving. So we are trying to combine a team with different areas in order to be really experts in computational design, design engineering, material science, and we really are focusing in to create the best visual communication possible to express our work. We conduct research in order to gain valuable insights to inform our strategies and our solutions. So this is a really critical step in our design process. Besides, we create and participate in events because we like to create meaningful connections. We like to collaborate. We need to get to know people. We like to expand our network because we believe that collaboration can drive positive outcomes. We explore and experiment new trends and technologies because by staying at the cutting edge of innovation, we can ensure that the problems that we are solving, the solutions that we are offering are the best of possible of today's technologies. And finally, we like to create visuals. We really engage our projects trying to create the best communication possible to ensure a lasting impact and the best understanding possible. We assist companies in crafting their unique recipes of solutions to enhance, modernize, and integrate new technologies into the daily design process. We have four focus sectors. Performance product design. In performance product design, we are focusing in creating the correct KPIs of your designs or your processes. So we go from data collection, data analytics, we create process automatization, we see how can apply our skills, our engineering, our knowledge in your products. We pride product performance, so everything that is about achieving a target, achieving a specific characteristic, specific material, specific, I don't know, like I'd say KPIs. That's the focus of our design part. Computational design process. This helps us to create. I mean, this is the part that for us is creative problem solving. So we create parametric solutions, so custom solutions, or generative solutions that are based in the creativity of our designers, in the creativity of the workflows that we are creating, also in the creativity of how can we utilize technology, mathematical formulas, and so on in order to create to inform our design. We are really proud of this part. We are focusing in creating a strong knowledge in simulations, either digital in implicit simulation, explicit simulations. We try to focus in create the best possible material setup, settings, and so on, in order to help companies to create virtual optimization, virtual prototyping, in order to create the best insights possible. Finally, we are focusing all these areas are converging in design for additive manufacturing because we know that the sector is evolving. So this evolution as it will be also an evolution in terms of manufacturing and something that we believe that it will be great and it will increase is the part of additive manufacturing. Well, after all saying all this, why design systems? Design is rapidly evolving, so it's becoming more complex. We need to see it from different approach in order to solve problems of today. So this starts to engage in different kind of collaborations. We need to create cross-functional teams in order to create a more complex solution, right? Because complex problems require complex solution. If we have different minds with different perspectives, that's the best way to approach it. So computational design is also good at this. It helps us to create this computational thinking in which it helps to breaking down systems into manageable parts and then discretizing into algorithms to enhance efficiency, to create scalability and adaptability. So we like to solve these kind of problems. That's why we are bringing today two study cases of two collaborations that we created across these last 2 years, 3 years. So the first one is ETH collaboration with Thomas Bockner, that he is a PhD candidate at ETH Zurich, in which the objective was to create a soft robotic hand using Inkbit technology with BCJ control, with BCJ, and the objective was actually to produce something that was similar to a human hand in order to see that it's possible with the use of multi-material 3D printing also achieve something as functional and complex like a human hand. So where do we start? We started from the image point, we created the mesh model, and once that we have this initial mesh model, we needed to start identifying what are the characteristics of the human hand, right? So we need to understand what are the ligaments, what are the bones, how are the bones bending, if they're like flat, bending, what are the tendons, what are the pulleys, what are the everything that it can be used to create a functional element. So once that we identify all of these elements that are actually there, at least we choose 5 of them, and then we're trying to create an intricate model with all of them. So we needed also to consider the manufacturing part. So we asked Indeed, and they told us like what to do, what not to do, how to create the interfaces between the soft and the rigid, how they do the grading materials, how they need to be blending together, and so on. And remember, this one is a human hand model, so the scale was small. So we needed to follow all this functionality in a human scale or like human hand scale with this material with minimum design requirements, and we need to create the best of it. So how do we approach the challenge? The first part of this challenge was to creating a 3D model. So we started with a traditional approach. We took Rhino, we placed our bones, and then we start creating on top of that. What was the problem of doing something like this? That basically, once that we finished, let's say, the first finger, because we needed to check if it was possible to create something like this complex, we understood that, okay, maybe we needed to move a little bit the poly, maybe we needed to change a little bit the belly, we need to change something. And this change something was affecting something else. So at the end, we create different options, and we saw that, wow, but if we need to change something, something was moving. So it was impossible to follow up all these design changes in a fast way because, of course, the timeline was tight. So we said, okay, let's remove everything and let's start from scratch. Let's identify what's the minimum characteristic element that actually can inform our design. So we understood that the capsule was the element that was ruling all of them. So once that we identified this one, we create a shape optimization algorithm in order to create the best fitting of the pulley, because we wanted to minimize the volume, but we didn't want any clash between the components. So at doing this, the best way was to create a shape optimization algorithm. We create the pulley and so on. After that, we start building on top of this element, because by building on top of the element, we knew that we were able to, for example, parameterize the thickness between the soft and the rigid, between the poly, between the tendons, between the all the ligaments. In this way, we have a more complex design based on a single structure. So what we did was actually identify what's that single structure, and then we create the model on top of this. So after 8 iterations, we achieved we reached the final result in which we have a model complex enough to create modify it and so on, and then you have some adaptability, so it can be adaptable. We need to rerun some parts, but of course there are some manual process like the training calls, like the sensor parts and so on. But at the end, the base model was created in a parametric way using these tools. After this, I decided, for example, what if computational design was today? So I took this challenge a little bit further, and then I created a simulation with all these multi-material setups. Why I wanted to do this? Because I wanted to highlight that from 2013, from 2024, it's changed a lot in the computational field. Now, for example, we have the meshless simulations by ETH Solutions, in which we can have multi-materials with faster interaction, and this helps us to create informed designs. So we know that maybe something is going to fail, something is not going to be correct, the ligaments are not well designed, and so on. So we can improve our designs. We can improve our boundaries. We can improve the resistance, and we can use it to create a better informed decisions. This is how it looks. BCJ printing actually is a BPA, a PNG, or like a bitmap image in which you have the grading colors from in grayscale, so you can select the different materials and so on. And then this one is the final result, in which we can actually see the soft robotic hand moving. And after adding on the mechatronic parallel actuators that was included by two of us. Okay, our second case study is about performance product design, because what could be best in terms of performance, as a sprint spark, of course. So this is a project collaboration with PUMA Innovation, with the PUMA Nitro Lab team, Carsten Wolfram and Coach Liv. So what do we did here? Actually, we took the challenge in how can we get a performance product, footwear product, using computational design, computational workflows. So we need to understand what the computational simulation has, what's the biomechanical information, what are the materials necessary to create all of these environments and push it into a product that actually can be informed and using these new tools. In order to do that, we need to create a workflow. So this is the workflow that we use, in which we try to create as much as possible of virtual simulations with finite element analysis in order to create as much as possible of virtual verifications, and then create middle steps of physical validations. Okay, we create a lot of tools. This is was really interesting, because I mean you see this spaghetti monster and so on, but actually it's not. It's a combination of a lot of clusters, of a lot of Python scripts. It's a really combinations of several templates, of several elements that actually we can modulate. We create for a specific tools, for example, to create data analysis, to create parametric design definitions, for creating definitive element setups, data visualizations. So we use all of this in order to also be able to create templates. And once that we identify what's the minimum requirement, we create templates, we create the characteristic elements that we can reuse in order to be able to analyze several data. So this several data needs to come from somewhere. So we started creating like experimental data collection provided by PUMA Innovation team. So we started to analyze how Carsten moves where. We create a data discretization, a data segmentation. We create different visual of this data in order to understand what was moving, where was moving it, and so on. So this enabled us to create. Okay, once that we created this, also we need to understand what the materials that are involved in this environment. No? What is the open, what is the carbon plate, what is the midfoot, the power plate, and the spikes. Also, we have the track that is a hyperelastic material, so we create the characterization of this material. We try to put everything together inside a virtual environment. What else do we need? We need to create engineering digital models in order to be able to simulate in a degree that is also biomechanical relevant, right? So we create engineered digital models of these different platforms. So this is one of the first results that we have after several hundreds of simulations, setups, and so on, time spent, readings, learnings, and so on. So we have this simulation. This is a high speed, 160 milliseconds, large deformations, high load, so we can identify critical areas, positionings, carbon plate direction, torsion, and so on. So this helps us to inform our designs. So this also helps us to interact between digital and physical products. So we use these simulations to iterate and create features. For example, the claw in the custom shoe. We use this simulation to identify what's the correct position, what is the takeoff angle. So we use this data to inform our design. We calculate the stiffness, we calculate the directions, and so on. So at the end, we wanted to highlight that by creating uh, virtual prototyping using data-driven design workflows helps also to reduce the physical sampling, which is something good for companies. Of course, we need to have really good material characterization because the quality of your inputs are as good as the quality of your outputs. We need to do model validations to understand how off we are between digital and physical and what needs to be improved, because actually this is an iterative process. It's a process that is always evolving. What's the result? Of course, he won the world championship, but of course everything is part of the athlete performance. But we believe that we help him with that milliseconds extra to achieve his goals. So by giving this extra push, this extra milliseconds with the claw, with the specific stiffness and performance setting, we help him to work to we contribute for his winning. What are our takeaways out of this design tool developments? It's important that now that design is evolving, is becoming more complex to create tools, uh, tools that can be repeatable, that has a meaning, that has a specific thinking behind. We realized that, we knew that virtual prototyping is complex, but it's something that we actually need to push because virtual prototyping is not reality, but it's close. It could be close. We just need to be sure of use the correct methods and correct material characterizations and so on in order to create really good informed decisions. Data visualization is crucial. Data visualization is one of the most important aspects of your design, because you could have a really good design, but you need to show it, you need to be able to express it to the big audience. And of course, computational design is a continuous learning field. So we are evolving, we are changing. Technology is also pushing the way that we are that we are using computational design, or how we are implementing. Also, the new generation of designers is pushing more for the use of new technology. So we need to be able to adapt to these continuous changes. Well, thank you so much for your time and your attention. This was our presentation. This is our data. You can find those either on our website. You can write me an email directly to design@moonrabbit.com. You can find me on LinkedIn. I will be happy to connect and talk more about this. And thank you so much for your attention.